Okay, we are live on YouTube. Should we start live on
Yeah,
YouTube?
let's start. We are live on YouTube. Yes.
Okay, start the recording as well, like just for a backup. All right, so let's begin. So yeah, we are very happy to have Gabriel Peyré with us. So Gabriel is a senior researcher at CNRS and also a professor at ENS Paris. He also holds like many other positions, like he's the deputy director of the Peyré Institute of AI, the director of ENS Center for Data Science. He was a former director of GDR at CNRS. And he also heads the Paris unit of ELIS, which stands for the European Lab for Learning and Intelligent Systems. So Gabriel, he obtained 2 ERC grants. He also won the Blaise Pascal Prize from the French Academy of Sciences in 2017, the Magnus Prize for the Italian Mathematical Union in 2019, and also more recently a silver medal from CNRS in 2021. And he's also the invited speaker at European Congress for Mathematics in 2020. So Gabriel's work mainly lies in the interface of applied math, imaging, and machine learning. And today he will be talking about scaling optimal transport for high dimensional learning.
Okay, thanks a lot. So it's a pleasure to be here. So I'm going to make like somehow a tutorial, I would say, on computational optimal transport, trying to explain a bit what is optimal transport from a computational perspective, and also try to insist on what can you do in high dimensions, what are the problems in high dimension, and some ideas to try to fix at least some of these issues. Also, what I would say today, if you want to know more about optimal transport, you can just go to this webpage or you Google computational OT. I guess you'll find this small book we have written together with Marco. So it's free, it's just a PDF you can download. So feel free to download it. And there are also lots of Python code you can use. So once again, feel free to use them. I guess it's a great idea to use Python, PyTorch, and so on to do numerics around the optimal transport. A bit of motivation. First, I would say that there are many application scenarios, both in low dimension, like for, I would say, maybe image processing or shape registration, and also high dimensional problems in machine learning, where you want to compare distribution of points or more general probability densities. It could be the colors of images. It could be some activity, for instance, on the brain. So these are on the left side of the figure. But of course, what we have in mind nowadays is high dimensional distribution. Typically, for instance, in natural language processing, one of the key revolutions of the last 5 or 10 years is the idea of embedding words as vectors and then manipulating vectors. For instance, if you think about transformers, language architectures, they do this type of computation where they operate on point clouds. And it makes sense to try to model this using some mathematical tools. And on the left would be mostly, I would say, maybe unsupervised learning or like representation learning, where you want to learn a model of a high dimensional probability distribution of images, for instance, in order to do maybe a resynthesis of images or to then do downstream tasks where you would fine-tune some networks that you have trained to model this huge collection. So typically, you would frame this as an optimization problem where you get some parametric model, alpha, that depend on the parameter theta. Of course, if it's a Gaussian, it's very simple, but you might have in mind that theta is like a deep network. And you're trying to, I would say, modify or deform your template alpha so that it becomes closer and closer from the data distribution, which is the big point cloud. So you could model this as an optimization problem where you want to minimize some discrepancy, capital D, between two distributions. One is discrete and one is typically maybe a continuous density or something like this. And the key insight of this talk is that you want to, in all these application scenarios, leverage some notion of metric, of distance between pairs of points. Could be the Euclidean distance if you do like colors, geodesic distance if you are on a surface, or could be some distance on some embedding space for NLP. And you'd like to leverage this, and basically optimal transport is a way to do this automatically for you. You should really think about OT as a lifting mechanism if you want. You input little d, which is a distance between pairs of points, and then it outputs capital D, which is the distance between group of points. Okay, and it is really what this mechanism I want to explain, which is, of course, you need to solve some optimization problems, so it's a bit intricate and costly, and also there are some issues in terms of statistics in high dimensions. So that's the question we'd like to study today. First, a bit of history. I would start with the basic OT problem, which is Monge problem, where you have two sets of points, xi and yj, the same number of points, and you'd like to find the optimal matchings, optimal permutations that minimize the sum of distance. And this is a combinatorial optimization problem. It was asked by Monge for military application, but of course, he was not really able to solve it. He was able to ask the question, but not to solve it. And this is, basically the history of optimization, which progressively leads to tractable methods to solve this problem. Okay, but initially it was like a very hard combinatorial optimization problem. More than this, the other issues is what do you do if you have a different number of points? So typically the key insight is maybe in some situation you'd like to be able to split points maybe in 2 or 3. And then the good notion is not the notion of point, of group of points, is rather the notion of distribution of probability. So you'd like to rather see the points as typically a distribution of probability, and then you'd be able to have some more flexible methods. Okay, and of course the biggest contribution in this area was due to Leonid Kantorovich in the mid-20s, which basically reformulated this Monge initial problem as a tractable optimization problem over the space of measure, over the space of distribution. So I would describe everything in discrete for simplicity of the exposition, which means I would have points, xi and yj, and these points, they would have some notion of probability, ai and bj, which are just histograms, positive numbers, and the sums to 1. So I would write everything using discrete notation and explain using like discrete explanation, but everything, of course, extends to arbitrary distribution. Okay, I would not really explain this, but basically you just replace the sums that you would see by integrals, and instead of dealing with discrete points, you can deal with arbitrary measures, arbitrary distribution. Okay, but in the discrete case, what is the contribution of Kantorovich, for which he got the Nobel Prize in economy, so it's kind of a big deal, is to describe this movement of mass, not using a bijection, but using a coupling. So what he actually, Kantorovich called this a transport plan, because it was for economic planning, which you can think of as just being a big matrix, or if you want a joint probability distribution. And each time you put a non-zero element in this array P, so if Pij is non-zero, it means you transfer some amount of mass. So basically here you see, for instance, on the first row, you have a single non-zero element, which means the first Dirac mass in alpha is going to be mapped to a Dirac on beta. But if you look at the second row of this matrix, you see that the second Dirac then is going to be split into 2 parts, which means you would have 2 connections that would emerge. And really, this is the big distinction with Monge. For Monge, it was a permutation matrix. Here, you could allow yourself for more general assignment between the point cloud, which is, of course, very important if you want to deal with a different number of points or points with non-equal masses and so on. So what are the constraints you have to satisfy? It has to be positive number, and you need to have conservation of mass, which means the sum on the row of P is going to be equal to A, which I can write in matrix notation as P times the vector 1 should be equal to A. It's very convenient to use matrix vector notation. And of course, you get the same on the other side. So P transpose time 1. So if you sum on the column, you get back B. So all the mass needs to be transferred. In this case. Just like the intuitive, I would say, the definition of conservation of mass. So these are the constraints. And you see now they are much more flexible because instead of having the set of permutation, now you get a polyhedral set of constraints because you have positivity and linear constraints. So you get a convex polytope in very high dimension. And now what does it mean among this polytope to select the optimal coupling, the optimal transport? You do the same as Monge. Okay, you minimize the total travel distance, which means each time you send a unit amount of mass, you pay a price, which is the distance, or more generally here, the distance to some power P. In fact, you could put any cost, but it's usually this type of cost that you would use. And then it scales linearly, meaning if you double the mass, you double the price. So it means that the total cost is just a linear function of capital P. And this is basically the birth of linear programming, one of the first, I would say, modern optimization problem ever considered. And in fact, at the same time as Kantorovich proposed this as a mathematical model for economy, and also develop duality theory. So I would not speak in my talk about duality, but Kantorowicz explained what is the economic meaning of duality. And this was a big deal for economic modeling. And at the same time, he explained this mathematical notion. George Danzig introduced the simplex algorithm, which you might all, I mean, probably most of you know about, which in this specific instance have a cubic time complexity. So it's really the combination of a new model, I would say, and a new algorithm, a breakthrough in algorithmic optimization that leads to very wide adoption of this type of approaches. And first, it was for the economic planning, but then everywhere you start using basically linear programming. Okay, so the good news is you can actually crack, I would say, Munch problem and solve it in almost cubic time. Okay, so so what's the big deal with this? So first of all, it gives you a transport matrix. So it's cool if you want to do interpolation or do assignment, which is quite interesting, of course, for economic application. But I think the reason why we are here today is that it's more than this. It's really defining a notion of distance. And the way to see this is if you take this cost of transport, the optimal cost induced by this problem, and you raise it to the power 1 over p, you get a distance, which is often called the Wasserstein distance. So first of all, it's a distance. Okay, it's 0 if and only if the two measures are equal, which is kind of obvious. What is less obvious is that it satisfies the triangular inequality, so it's quite a nice proof. But you might argue, okay, I know tons of other distance over probability distribution. Why should I care about this one? So the first way to look at this is to look at basically the topology induced by the Wasserstein distance. And you can show, and this is actually a theorem, which is this theorem, is that the topology induced by the Wasserstein distance, so basically what does it mean for two distributions to be close to get one from each other in terms of Wasserstein distance, is just the topology in probability, we would say the convergence in low topology. So here, for simplicity, I'm assuming I'm on a compact domain just to avoid problems that mass that would go at infinity. But at least if you're on a compact domain, this is really the notion of convergence in low. So basically, if you view alpha and beta as the density or the distribution of some random vector, the convergence in Wasserstein is equivalent to the convergence in low. So kind of a weak notion. So in analysis, maybe people would call this the weak star topology. So it's kind of a weak topology, a very flexible topology. So maybe a way to have some insights about what this topology is about. So it's basically the topology, if you speak about convergence of central limit theorem. So central limit theorems is a notion of convergence in low, a weak notion of convergence. You could have discrete vectors that would converge through the central limit theorem to a continuous density, to a Gaussian. So you really need something that is very weak and very flexible. And a way to look at how much is it flexible and how much is it geometric, I would say, is to contrast this with a more classical or simple notion of distance, which is the total variation distance between two measures. And the total variation, if you have two densities, is just the L1 norm. So basically, the total variation is just the L1 norm between the distribution. It's called often the strong topology because L1 is basically somehow the dual of the L infinity norm on continuous function. So it's really the natural notion of topology induced by duality, by the duality between integration duality between continuous function and probability distribution. And the L1 norm is very strong. So you can look at it just in the simple case. If you look at a single Dirac, that would progressively shift toward its final destination. So if you look at what is the total variation between two Diracs that are not at the same position, of course, then the total variation norm is just equal to 2 because you have +1 and -1. So the L1 norm of the difference is just equal to 2. So in terms of the strong topology, basically a discrete Dirac never converges to another discrete Dirac. It's always equal to 2. More generally, for the strong topology, a discrete measure can never converge to a continuous distribution. So the central limit theorem is not true in total variation. In sharp contrast, if you look at the Wasserstein distance between two Dirac masses, there is a single way, of course, to send a Dirac to another one. And since you raise to the power p the distance and then to the power 1 over p, you see that the Wasserstein distance between two Dirac is equal to the ground distance itself, to little d. So this is really the meaning of the lifting mechanism. The lifting mechanism means that you give me little d between position, maybe, between x and y, and then I give you a distance between arbitrary group of points. But when I evaluate this distance on single Dirac, I get back the original distance. And you can basically show that it's more or less the only formula or the only way to have this nice property, this nice one-to-one, I would say, injection of points into distribution. And it is one, I would say, strong reason for using Wasserstein is you get this like very natural lifting mechanism, and also it's somehow induced a notion that is very nice for many applications. Of course, I would say for theoretical questions, but also for practical purpose, since in many applications you want basically the distribution to be able to move, to shift, and to be robust to this type of shift. So I would say this is the main motivation for introducing Wasserstein method in data science and machine learning. Okay. Now just one slide to recap a few algorithms that maybe you have already heard about. I will not describe the algorithm, and just like name dropping, so that you know they exist. The first one, of course, is just a simplex algorithm, which has complexity basically n cubed log n squared, which is good, but not so good, of course, because if n is very large, it's still quite slow. A particular case that is very important is the case of Monge. If you get two groups of points with unit mass and the same number of points, then you can actually show, it's called a Birkhoff-von theorem, that the solution to Kantorovich, or at least a solution of Kantorovich problem, is a permutation matrix. So it's also a solution of Monge problems. So in this very particular case, you get a one-to-one, I would say, bijection, and the transport plan is just a bijection. And in this case, you can use the Hungarian algorithm, which is very famous. So you can look online on Wikipedia. It's a very nice algorithm, which is a bit faster. Another case, even simpler, I would say, is the 1D case. If you have two distributions in 1D, you can show that the optimal transport is a monotonic map, which means you can obtain it by simply sorting the blue and the red point from left to right. So in 1D, the complexity of optimal transport is basically n log n. But of course, it's not true in 2D. If you look at the paper of Monge, more than 200 years ago, he already knew this, and he made nice picture, nice drawing of why it's not so easy, in fact, in 2D to solve the transportation problem. And he was not able to solve it. I would just like say a few words on some special case. First one, the case of Monge, actually, if you take the Euclidean distance to the power equal to 1, then you can reformulate the problem as a mean cost flow, for which you would have a faster algorithm, like mostly n square algorithm. Another case is in the case of the Euclidean distance to the power 2. Then you can solve the optimal transport by solving basically partial differential equation using finite element and so on. This was discovered mostly, I would say, by Jean-David Benamou and Yann Brenier, who wrote a nice paper about this. So this is on the left, the geodesic between Jean-David and Yann, where the mass is basically the black pixels. So it's totally useless, but it's to illustrate basically the transport mechanism. And another thing I want to mention is recent papers by Quentin Mérigot, but it's actually much older, is a semi-discrete case where you want to map continuous densities toward discrete points. In this case, it's quite natural to understand what's happening. You're going to have cells that are going to be transported to points, and the goal is to find the shape of these cells. And you can show in the Euclidean case to the power 2 that these cells are actually Voronoi cells. And it turns out that you can compute in linear times Voronoi cell in 2D and 3D, which gives you algorithms that are, I would say, a state of the art in 2 and 3 dimensions. And that's very nice. Now, what we want to speak about today is not about all of this. We basically want to tackle a case where we don't really care about having high precision computation for the optimal transport, because we have random points, we have sampling noise. Also, well, maybe we are using optimal transport for downstream tasks that don't necessitate very high precision. So I think in most situations, you don't really care about having high precision solver. And this is the type of situation I want to explain now. So I would like to explain one algorithm that you can take with you and implement very easily. And this algorithm actually is very old. You can trace it even before actually Kantorovich through previous work, for instance, in statistical physics, statistical mechanics. First, I would say it appears in the work of Edwin Schrödinger that was describing in statistical physics basically the evolution of gas. So it's often called Schrödinger's problems. And Schrödinger was using it to answer the question of you have two basically distribution of particles of gas at two different times, but you basically don't know how they have been evolving. And your goal is to guess the most likely trajectory. But the key modification with respect to optimal transport is molecules of gas, they don't move in straight line. They are actually like stochastic Brownian motion. So they would not move according to a deterministic trajectory. And if you introduce the temperature epsilon, what he proved in his paper, is actually the connection between the two sets, the most likely, I would say, connection between the two sets of points is obtained by solving a modification of the Convergence problems, where you add minus the entropy. So you add epsilon times minus the entropy. It's the classical Shannon-Boltzmann entropy. So it was even before somehow Shannon. So it's really like something that is visionary, I would say. And you can use the temperature as a Lagrange multiplier, basically, between the classical optimal transport problem and some entropic penalty. So like a maximum entropy method, if you want, to estimate optimal transport. And maybe, and you can basically use this like a barrier method, like epsilon times Pij log of Pij will really act as a barrier. So will enforce positivity of the coupling. But maybe a simpler way to look at this, at least if you're not an optimization people that are familiar with entropic barrier function, is to look at the solution. So as soon as the temperature is strictly positive, so if epsilon is strictly positive, basically it's really what's happened in maximum entropy method. The solution would be strictly positive. So you would have capital P that is non-zero everywhere. So in order to understand what's happened, we just draw a little segment. Each time there is a Pij, which is larger than here 10 to the minus 3. So if you set epsilon to 0, then you get back optimal transport, of course. And as I said before, you get a bijection. You get a solution to Monge problem. But as you increase epsilon, you see more and more connection appearing. So somehow the matrix becomes denser and denser. And if you, and we'll see this together in a few slides, look at the limit when the temperature goes to infinity, you would basically connect everyone to everyone. So you see really the effect of entropy is increasing the number of connections. So you might argue, why is it useful to do this? It's useful for two reasons. So somehow get the best of both worlds. First of all, and I would explain just after, you get a fast algorithm. And as you increase epsilon, the algorithm becomes faster and faster. So somehow it's the first benefit of entropy, it's having fast algorithm. The other benefit, which I think is at least as important, is that it stabilizes the solution. So it gives you solution capital P, which are very stable. So for instance, which depend in a very smooth way on the inputs, xi and yj. And this stability is really the key in high dimension to have statistical efficiency. So we'll describe this later, but it's really the way to cure somehow the curse of dimensionality. You can interpret this as like a smoothing, if you want, or a diffusion effect. So in high dimension, you really need a lot of diffusion in order to have quantity that you can estimate robustly with not so many points. So really, the benefit of entropy is computational and statistical, and they really work hand in hand. And this is what I want to explain now. Okay. So now we go to the core of the talk, which is how you compute this solution and why this solution has good property. So the algorithm to compute this solution has many names. It's actually very old. I like to call it Synchron's algorithm because Synchron is the one that made the mathematical analysis of the algorithm. But in fact, it's even older than Contorovich. So it's an algorithm that is really, really old. And the way to derive it, actually the way I like to derive it, is the way most people would attack maximum entropy problem, is basically to introduce Lagrange multiplier for the constraints and to write down the optimality condition. So if you do this, so it's not very hard, you will discover that you introduce two Lagrange multipliers, u and v, which are positive quantities, so two positive vectors, because you basically have two constraints. And you need, of course, to satisfy the constraints, of course. But you see that you are going to be a solution, capital P is going to be a solution, if and only if you can write this capital P in exponential way. So people would call this like a Gibbs distribution. And what does it mean in our case? It means that you should be able to write P as a diagonal scaling of a Gibbs kernel. And I would explain what it means. The Gibbs kernel is capital K. It's just a big matrix, okay, which is exponential of minus the cost divided by epsilon. So if you think, for instance, of the Euclidean cost to the power 2, the Gibbs kernel associated to your problem is just a big Gaussian matrix. So think you have a big Gaussian matrix from your data. And then you need to find scalars ui and vj. The u would get would multiply the rows, and the v would multiply the columns. Okay, so you need to find u and v, so diagonal scales, that scales your matrix so that it satisfies basically the constraint. So the first instance, and probably the most important instance of this problem, is when you have uniform distribution. So the Monge problem. If U and V are equal to 1, then capital P should be a bistochastic matrix. Okay, and the fundamental question which is raised on the right-hand side is whether you can scale some positive matrix, some positive kernel toward bistochasticity. Can you normalize by row and column operation a positive matrix so that it becomes bistochastic? And it's a very old problem that you encounter each time you need to normalize somehow a big array of numbers. And in fact, people were studying this even before the age of computer. And they actually invented the algorithm I will describe much before optimal transport. Okay, and the first thing we can say, which is already a nice result, is because the original optimization problem is actually strictly convex, because the entropy is strictly convex, capital P exists and is always unique. Okay, so by simple convexity argument, you have the first nice result that there is always a way to scale toward bistochasticity, and this way is always unique. You have a unique way to scale toward bistochasticity. But of course, the question is not can you do it, is how do you do it? So how do you do it in practice to compute this capital P? And I think the best way to introduce this idea is by just heuristic rezoning, which was what people basically did before Synchron, is you look at the constraint and you look at what is your P. Your P is basically the multiplication of diag of U, so diagonal matrix with U, K, times diag of V. And you multiply this matrix by 1, so you just sum on basically the rows, and you should obtain A. So if you look at the computation, you obtain this first equation, which I call here in red row constraint, is that U multiplied by KV should be equal to A. And you see this little dot with a circle. Here it's just classical, I would say, multiplication of two vectors, so entry-wise multiplication of two vectors. But of course, when I write K times V, I mean the matrix K times the vector V. Okay, so you get the first equation. And then, of course, you get the second equation by simply exchanging the role of U and V. And you see that, in fact, solving this Schrödinger transport, maybe call it like this, is as simple or as difficult, probably, as solving two polynomial equations of degree 2 in U and V. As many equations as unknown. The good news is it looks simple, but of course, it's very high dimensional equation. So it's non-trivial to solve polynomial equation of degree 2 in very high dimension. But the nice thing is they have really nice and favorable, I would say, look if you view this as a question of finding U on the left-hand side. So basically, if you give me a V, of course, I can compute U very easily simply by dividing A by KV. Now you get U, of course, you plug into the second equation, and then you get V the same way. So you see that now we have turned the initial problem into a fixed point equation. We apply this fixed point iteration, and we hope it would converge. And this is what people have done for years, for actually almost like 50 years, because before actually Synchron proved the convergence. And Synchron didn't only prove convergence, it proved that actually these iterations are contraction. They contract for a very famous metric, actually famous for people that do Markov chains, which is called the Hilbert metric. So the Hilbert metric is basically the infinite norm on the log. So it's like a modification of the L infinity norm, if you want. And what you can show is that actually these iterations are contracting. And in fact, the proof is exactly the same as the one you would do to prove a Perron-Frobenius contraction, so convergence of Markov chains toward equilibrium. And really the trick that was remarked by Synchron is that the only difference with the Markov chain is the division. If you didn't have the division, everything would be linear, and you would be facing convergence of a Markov chain. Here, the division is harmless because you can show it's the isometry for the Hilbert metric, basically because of the log. So this is very nice, and by applying the same proof as for Markov chain, it proves convergence. So it's reassuring. So this is the good news. The bad news is, of course, convergence is very slow if epsilon is small. So as epsilon goes to 0, the kernel becomes degenerate, and the contractance becomes less and less efficient. It's like a Markov chain that would not be basically diffusing enough. So at some point, it would go so slowly that you cannot even use this algorithm. So the good news, I would say, is in practice, and it's what I want to explain after, is you really want to use this algorithm where epsilon is not too small. for many reasons, including statistical reasons, which means that this algorithm in practice converge actually quite fast. So it's really an algorithm that you want to use in cases where you don't really want to solve with high precision optimal transport because epsilon would be quite large, but you want to favor a lot of smoothing, and also you want to favor an algorithm that has nice computational properties. Basically, the only computationally expensive part is the matrix vector multiplication. So each iteration costs n squared, which is, I mean, good or bad. I mean, there's no, and n squared can be quite large if n is large, of course. But the nice thing is it's something that parallelizes very nicely on GPUs. So it's really an algorithm that is designed for modern hardware, I would say. And this is the insight that was given by Marco Cuturi. So Marco Cuturi wrote a quite influential paper that explained that Synchron is really the way to go if you do machine learning. Now you could refine a bit the analysis, which I will not do because I don't have time, but you can basically leverage classical ideas from mirror descent. So for those who do convex optimization, it's like some kind of a nice connection with mirror descent. And mirror descent is known to converge basically at rate 1 over the number of iterations. And by leveraging the convergence speed of mirror descent, you can actually show that if you want to approximate basically optimal transport to some precision, you can choose epsilon to be equal to the precision. So epsilon will be the precision. And the number of iterations you need to make to reach this precision is actually 1 over epsilon squared. So the total complexity of optimal transport in this framework, assuming you want to approximate optimal transport, which might not be your goal, I mean, it's just a goal you might want to try, is n squared divided by epsilon squared. So you see the good thing is the n squared. The bad thing, of course, is the epsilon square, which might be, of course, very slow if epsilon is small. But this is basically the trade-off of Synchron for practical purpose, is n square divided by precision square. Okay, so this is about the algorithm that I really recommend you use. The other thing is, of course, it's very simple to implement, much simpler than simplex or like interior point method and so on. So it's something really almost anyone can implement in a few minutes in Python. There is also a dedicated library to do this, so there's many options for you. Now there is more in this. One thing that I just want to mention, I would not really discuss it, is there's many more extensions of Synchron that you can use to solve many other problems related to optimal transport. So this is just a nice example that I enjoy very much due to Guillaume Carlier and Marshall Haguet, which is the computation of Barry center, which is kind of a convex optimization problem where you want to minimize basically the sum of Wasserstein distance to compute some Barry center between histograms or between I would say distribution of probability. And you can show, actually, we showed in a paper with Guillaume, that you can also use Synchron to approximate this problem. And this gives you an algorithm that is very similar, I would say, to the original Synchron, except now it computes Barry center instead of just computing an optimal transport. And there's many other problems you can tackle this way. Maybe, for instance, gradient flow can be obtained this way, or other problems related to transportation or game theory can be tackled with this type of tool. Now I want to I would say switch to another class of question, which is not about like how fast can you compute optimal transport, but how precise can you be in high dimension? And of course, they are interplayed between, if you have a faster algorithm, of course, you could go to high precision. So it makes sense to study both together. But really, one fundamental question is can you really use it in high dimension? The first thing to notice, it's not really a good news, is that, of course, because of this extra anthropic term, it's not a distance anymore. So in particular, the cost of Schrödinger between alpha and itself is non-zero. And if you look numerically, this epsilon will cause you a lot of troubles. In particular, I mean, very simple case, if you just want to solve, you give me some alpha and you want to find the beta that is, or whether the opposite, you give me some beta and you want to find the alpha, which is the closest to beta, you'd find a solution which is not equal to alpha. You find something that is somehow biased toward the mean. So if you let epsilon goes to plus infinity, you'd recover that the optimal alpha is simply a Dirac located at the mean. So it's getting very, very bad, of course. So we somehow call this the entropic bias, if you want, the fact that the entropy gives you a bias on the estimation if you want to use optimal transport for other tasks. So it was a major issue, and we tried to somehow address it, and we came up with a very simple, I would say, formula that does the job very nicely, which was introduced in a paper of Marco Cuturi and collaborator, which is like a polarization formula, at least the way I've used it. It's just simply subtracting 1/2 of the Schrödinger cost between alpha and itself and beta and itself. So we often call this the Synchron Divergence. And it's a quantity that is, of course, 0 when alpha is equal to beta. But you might be worried that we have negative sign, minus sign. So initially, I would really think that this would never work because of the minus sign, things could get very ugly. So we did try first numerics on this, and it was really working nicely. And we started investigating the theoretical property of this very simple de Viazing formula. And we came up with several results. So one of which is that we were able to prove that it's positive. For instance, on Euclidean space or more general space, you can show that this quantity actually defines a positive value. And that it's actually metrizing the same topology as before. So it's somehow metrizing also the weak topology. So, okay, I don't know if it's a very strong result, but at least it's something that goes in the correct direction of showing that this quantity behaves like an optimal transport quantity. Another thing you can look at is look at what happened in low temperature and in high temperature. So for the low temperature limit, it's something that has been studied a lot, the low temperature limit of Schrödinger problem in the large deviation community. So there's a whole community studying this problem, led by Christian Léonard, for instance, and we also did a paper with Guillaume Carlier and other people to study, in fact, not only that it converges to Wasserstein distance, of course, but how fast do you converge and what can you say about the convergence. The other thing that is actually also very intuitive that we studied with Onjedve is the large temperature limit, in which case you can show that actually the Synchron Divergence converges to Euclidean distance, simply Euclidean distance, which might be obvious, but actually it raises a nice question: is what actually are Euclidean distance between probability distribution? In fact, this is an own field, I would say, of statistics, led among others by Arthur Grayson. It's often called maximum mean discrepancies, or MMD, and often also it's called kernel norms. So basically, I would not explain this in details. It's defining kernel norms or kernel space or reproducing kernel Hilbert space over probability distribution. And the way to do this is to pick your favorite kernel and to use this kernel as a matrix when you want to basically compute the inner product or the Euclidean distance between two histograms. Okay, so usually I would say people would maybe use the Gaussian kernel, but if you look at what happened with this Schrödinger cost, the kernel you obtain is actually quite weird, or maybe quite weird for people not into MMD. It's simply minus the distance to the power p. And in fact, this kernel, despite it has a minus sign, defines positive quantities over probability distribution. So if you want to look at it, it's called conditionally positive kernel. And you can show that if D, for instance, is the Euclidean distance, this is actually a valid kernel. It's actually a quite famous kernel. It's often called the energy distance kernel when P is equal to 1, or the Kramer norms. It's kind of, I mean, maybe not famous, but at least something that has been used a lot. It's much simpler than Gaussian kernel. So if you ever encounter probability distribution and you want to compare them very easily, I would really recommend using this kernel and not using a Gaussian kernel. It's much more stable and simple to use. And for those who do PDEs, or at least are more into analysis, you might recognize that minus the Euclidean distance to the power p is basically the green kernel, the fundamental solution of a Laplacian or of a fractional Laplacian. So I will not get into the details, but this distance or this norm actually, it's a Sobolev norm. So it's an inverse Sobolev norm. So if you are into reproducing kernel in Hilbert space, you might also enjoy Sobolev space, and this is just basically defining a Sobolev space. So you see that, not getting into the details, but this epsilon parameter is really a way to interpolate between two regimes or two different types of metric, which one is a very non-Euclidean and very actually not even a distance, which is the Wasserstein norm, Wasserstein distance, sorry, so it's not a norm. Unless P is equal to 1, but in general, it's not a norm. And if you let the temperature goes to plus infinity, you get back a Euclidean space, so a totally flat space. which is arguably simpler, but it doesn't have all the nice geodesic interpretation or geometric interpretation as optimal transports. And you can view basically this diffusion parameter as a way to interpolate between these two types of very different metric over the space of probability. Okay, this is nice, but okay, you might argue which epsilon should we use? What is the best method? I would basically not answer this question, but I can actually give you at least some insight that you should never use an epsilon that is too small if you are in high dimension. What's the reason for this? The reason is actually quite well known, at least starting from the work of Dudley in the 60s, that basically proves this theorem that I wrote here, is a question of sample complexity or discretization, I would say. In most problems, instead of having directly access to alpha and beta, unless you are in like 1D or 2D, but in general, you never have access to the true distribution, you get access to some kind of sample. And the easiest way is to assume that you have access to identically distributed samples, alpha hat and beta hat, n samples. And you might question what is actually the error you make in terms of just estimating the Wasserstein distance. So maybe you might use it for more complicated tasks, but obviously, if you're not even able to compute the Wasserstein distance, you might be in troubles. And the answer is very bad. Is you can show that for this estimator, and in fact for any estimator computed from endpoints, the error you make is of the order of 1 over n to the power 1 over d. And it's actually sharp. You cannot really improve over this. So they're also matching lower bound, which means that unless d is super small, and unless someone tells you more properties, of course, about your distribution, you might never be able to compute it. So even if they are drawn from like uniform distribution on cubes, if you are on a high dimension, you might never be able to tell they come from cube. I mean, unless n is like gigantic. So this is the bad news. There is a curse of dimensionality of optimal transport, and it's very clear. So there's many workaround. Of course, if you are on a manifold, maybe D might be quite smaller, but still, of course, in most scenarios, you cannot assume that D is small enough for this method to work. On the other end of the spectrum, if you look at Euclidean norms, like MMD norms, they are just sums. There is no optimization problem, it's just sums. So you can view MMD norm or Euclidean norm over discrete vectors as just being like a Monte Carlo method to estimate continuous integrals. It's a little bit more complicated than this, but the take-home message is Euclidean norm don't suffer from the curse of dimensionality in the same way that Monte Carlo method don't suffer from the curse of dimensionality. It might not still be usable in high dimension because in the big O, you get usually huge constants. But in terms of convergence with n, you get the convergence rate, which is 1 over square root of n, which is a classical rate for Monte Carlo method. So you see really that you have two quantities, Wasserstein norms, Wasserstein distance, and Euclidean norms that behave very differently in high dimension. So this raises a natural question that we have studied with Augenvey of what is the statistical complexity, the sample complexity of this cost of Schrödinger. And the good news is as soon as epsilon is strictly positive, you don't suffer from the curse of dimensionality in the same way that Monte Carlo don't suffer from it, in the sense that the speed is 1 over square root of n. But of course, the bad news is the constant which blows with epsilon and which blows inversely proportional to the dimension. So somehow there is a no free lunch. So the take-home message of this theorem, which I think is quite a nice theorem, but the take-home message is not always as good as we wish, because of course, you know that you cannot improve over the first equation. So if you want to use Synchron to estimate optimal transport, you would still face the curse of dimensionality, of course, because you would need to tune epsilon inversely proportional to n, and then you would get back the original complexity. And we'd study this in details in a paper with Flavien Léger and Lénaïque Chiza and Pierre Roussillon, sorry, don't forget about Pierre, where we proved actually this bound, and we studied in details actually the computational speed. So because this is like rates, but now you ask the question, what is the algorithm and what are the complexity of this algorithm? And of course, then Synchron is useful. Synchron is definitely faster than the simplex algorithm. But if you really want to estimate optimal transports this way, it's just not possible. You really need to leverage other properties of your distribution if you want to break the curse of dimensionality. So this is, I would say, one important message is, I mean, basically don't use epsilon that is too small. And in practice, for more complicated tasks, you might need typically to cross-validate epsilon, or at least to have some heuristics to set up this value of epsilon. So this is it about, like, I would say, the mathematical theorems that I wanted to show you. And now I wanted to conclude with maybe more heuristic application or some perspective maybe for future work. One of which, I mean, of this application is basically generative models. So I would not really teach about generative model. It's something that people are very interested in I would say, deep learning. So I would not get into the details. It's mostly an excuse to speak about this type of problems and why optimal transport is actually useful. So I've already explained the type of scenario we want to deal with is like parameter estimation from point observation, point cloud. Of course, the simplest approach or the canonical approach would be to assume that your model alpha has a density rho with respect to maybe Lebesgue or something else, and to form the minus log likelihood, which somehow, I mean, a way to interpret this is, at least if the number of samples is large enough, it's like minimizing the relative entropy or the Kullback-Leibler divergence between your observation and your model. Okay. So it's nice. There's a lot of nice formulas, sometimes closed form, or sometimes you need an algorithm to solve this. But which is the key constraint is this idea that all the alpha should have a density with respect to the same, I would say, reference measure. If it's not the case, then usually the maximum likelihood doesn't even exist. And a typical scenario where this hypothesis will fail is in generative modeling. What is generative modeling? I would say it's something very old, but there is a renewal in this idea, is the fact that you might not want to write explicitly the expression for rho or for alpha, the density of alpha, but you might want to model your problem simply using an algorithm. And how does this algorithm operate? It samples random instances from alpha by simply drawing a vector in low dimension. So zeta is the, would say, some distribution, maybe a Gaussian or uniform distribution in a low dimensional latent space. And then you send this sample in high dimension using a deep network. So G is somehow something that would increase the dimensionality from latent space to high dimension. And of course, the problem is then the distribution alpha would be very singular. And somehow by changing the network, G, you want to make this surface alpha as close as possible to the data. And this is really why you want to use a loss function that operates as a matching mechanism and not as a Kullback-Leibler divergence, which would be basically plus infinity everywhere. And there is a long stream of work that propose to use distances like the Wasserstein distance or related distance in order to define estimator. But of course, the problem is then it becomes much more complicated to solve. You never have closed form, and it becomes an optimization problem, and it's not trivial. So of course, it also raises tons of interesting and totally open questions. But you see the idea is to formulate estimation as a minimum Wasserstein distance problem. For most scenario, you would use a generative network. So I would not teach what is a generative network. If you have never encountered this before, it's basically like a traditional neural network, but that you would play backward. Instead of using a network to induce a low-dimensional representation of your data, you do exactly the opposite. You start by a low-dimensional latent vector Z, and you progressively increase basically the number of pixels until you reach high-definition images. So you can use this generative model as somehow methods to gain in resolution as you go deeper and deeper. This is kind of, I would say, bird-eye view overview of what is this trend of generative modeling. And now the goal is to train the network. And now you are in big problems because this is hard in many, many ways. First of all, because it's an infinite optimization problem, or at least the Wasserstein distance operates between the distribution alpha, which is the parametric density, but which is basically defining a continuous densities. Beta, okay, it's discrete, but it's also very large. So you might also want to sample it. And it's non-convex and so on. I would say the way people would solve this problem heuristically, is to use a stochastic gradient method. So, which will simply at each iteration draw random sample from your model and random samples from your data. But of course, you are in a situation where you are not really allowed to use stochastic gradient descent because the gradients are not unbiased and you don't really know what is the error you make. So there's many aspects that are not really, at least up to now, well understood. But this is what people would do, nevertheless. And then in practice, you would code this in PyTorch or TensorFlow or JAX or whatever, and you let the optimizer or the package compute the gradient for you. So you see really the computational graph is quite impressive, but actually it's nice because you really have first a neural network to compute your model or to draw random sample from your model. And then you compute the Gibbs kernel. And then you run another, if you want, recurrent network, which is implemented in Synchron. You can really think of Synchron as a neural network on top of another neural network, and then it gives you the loss function you want to minimize. Okay, I don't need to say that, of course, it's very complicated. There is no real mathematical theory that explains what's going on. If you test on small digits, so sample digits from MNIST, you get very good results, but there's no need for such complicated things. Many other methods would achieve similar results. Now, if you use it on more complex images, it's a disaster. It basically doesn't work. And the reason is quite simple to understand. The reason is if you look on images, using the Euclidean distance to compute or to compare images is not a good idea. Euclidean distance doesn't work at all to compare images. So the thing you should do then is to try to somehow learn the metric or learn the embedding of the image in order to compute some metric. And this idea of training basically a neural network also to compute the embedding of the image or of whatever things you want to synthesize is really linked to this contribution of Jan Goodfellow and collaborator, which is called Generative Adversarial Networks, which you probably know, which is this idea of if you want to achieve good quality samplings through neural networks, or at least through generative neural networks, you need to train two networks basically. And you can do this using optimal transport. It's not the way it was initially designed in GANs. In GANs, they use another type of distance. And it's not clear what optimal transport brings here. People have argued it brings stabilities. It's also easier to train somehow. But it's mostly open question, I would say. Mostly a question about what is the impact of epsilon, what type of metric you should use, what is the impact on the final, both quality of images, but also the quality of the distribution itself. So what people mostly would do, I would say, is to have visual inspection about the quality of the synthesis. And it's really not what optimal transport is made for. So optimal transport is not about the visual quality, which here is okay. Of course, it's not the last test result. So it's a paper from a few years ago at iClear. Now you get even more impressive results, not even using GANs. So now they use other type of models. But the question of optimal transport is more about the statistical quality of the overall set of samples. And of course, it's a bit like a chicken and egg problem because I've already said to you that it's very hard to estimate optimal transport in high dimension. So we are a bit stuck, of course, on this type of question. But okay, let's try to conclude with more, I would say, promising ideas for future work. The first thing is I think there is this trend of going to using optimal transport in high dimension, and I think there was a lot of work from mathematicians that are very interesting and illuminating, but that don't deal with the high dimension. So all these theories that exist of Yann Brenier and follow-up work of Figali, for instance, are really restricted to low dimension because they impose constraints that are totally unrealistic in data science. They impose convexity constraints, they impose smoothness constraints. Now the question is, what should be the good constraint you want to put in order to do optimal transport for the next century, for the century of data science? And it's not totally clear, actually. So this raises a lot of questions about the key hypothesis you want to put and what should be the good algorithm. Is Synchron a good algorithm or not? Can you improve it? And so on. There is also a question about learning the cost, and question on some problems where you don't even have a cost. Maybe the data set actually belongs to different spaces. This is an example I like a lot in genomics, where you acquire samples in two different spaces because you have two different types of recording of the genomic content of your cell. So here, each point would be a cells. And now you have the question of fusing together basically a big collection of cells that are obtained through biopsy. So two samples here would be two biopsy of the same patients, and you know they come from the same patient. So you should be able to somehow relate them together. And one of the ideas that I've been studying a lot recently, that was introduced by Facundo Memoli a few years ago, is the idea of modifying optimal transport in order to take this into account. And you can do this basically by changing the optimization problem. Instead of solving a linear problem, now you would solve a quadratic optimization problem. Now the question is that it becomes non-convex, and it becomes actually NP-hard to solve. So you are like facing the difficulty of you're not solving a linear program. And it raises a lot of interesting questions, and in practice, it seems that heuristic algorithm, or at least algorithm that compute a local minimizer of this quadratic optimal transport, do really good in practice. So it raises a lot of questions about, studying this type of extension, and I think it's quite stimulating. Sorry for speaking maybe too much. I would stop here, and I'll be happy to answer questions if you have.
If you have any questions, like feel free to unmute yourself and ask. Like other than Wasserstein's distance, like are there any other distance measures which go like across, like any other established distance notions that go across like something like heterogeneous data?
So you mean like, distances between like distribution that would have similar properties, or?
Yeah.
I think to be honest, the simplest one and the one you should try first before optimal transport is maximum mean discrepancies. So maximum discrepancies is basically this formula here, this one. Here it's written in matrix notation, but this is basically a kernel norm. So you would take your samples and you would just integrate the kernel. So it's basically a sum on all the pairs of samples. It's simpler. It's a closed form. It's n squared, and it already gives good results. In practice, somehow many tasks, I would say, optimal transport improves a bit. Sometimes improve quite significantly, but it comes with a lot of cost and more difficult mathematical questions. So of course, maximum mean discrepancy are simpler, older, and they really are very different from optimal transport, because instead of looking that each point should be mapped to a single point, these kernel norms, they simply map each point to all the other one. So it's really like each point is going to be compared to all the other one, which you can see as like a very simple and very brute force way to compare two group of points. So my short answer would be yes, and actually this is like basically the first thing you should try. And then I think it's a good idea to switch to optimal transport, which would be more costly, but sometimes give better results. And you can look maybe in the webpage of Arthur Greton. I think you have a nice, I would say, nice review paper on MMD. And there's a lot of, since it's just summation, everything is much easier. Like all the theory of MMD is very quite simple. Like including like this type of theorem is quite also easy to derive. Another way to design distances between probability distribution is to pick your favorite divergence, like L1 or whatever, and just to apply a smoothing to your distribution. So this would be the way most people that don't want to deal with computation would do. They would take their distribution, they would smooth the distribution using a kernel density estimator, and then they would use L1 on top. But the question is, in high dimension, it becomes very hard to compute kernel estimators. So I don't think it's something that would scale in high dimension. But the most naive way to design smooth estimator for measures is to pick any norm you like, L1, L2, whatever. And of course, you cannot apply it directly because L2 is not even defined on Dirac. But what you can do is you simply smooth your distribution. It gives you a nice function, and then you can use your favorite method. So, if you want something simpler, it would be the way to go, but it's not something you would face huge difficulty to compute it in high dimension. So if you care about computation, I think it's better to just like switch to a well-defined method such as optimal transport. But yeah, it's more or less. I don't know if it answers your question, but
Yeah, it does.
but you see,
Yeah,
there's definitely many options. But
yeah.
optimal transport comes with a lot of nice properties, and it's like a canonical notion, and and I didn't explain, but there is also a very nice connection with partial differential equation, with evolution of densities. Well, depending on what you like, you find a lot of other like nice properties, which in itself, I think, is a reason to study optimal transports, because there are so many nice, I would say, outputs that maybe not in statistics, but in PDEs. And also, maybe I should mention that there are also, many interests recently in using it to study, like if you train a neural network, you might want to use optimal transport to study the dynamics of the neurons. There's some papers recently that have been trying to study the convergence of neural networks training using basically Wasserstein flows. It's quite also nice. It's very theoretical. It's probably not very relevant for application, but it might be a way also to study evolution of group of points like neurons during training.
Are there other questions? Now we can take questions offline, maybe. Yeah. Mm-hmm.
Yeah, maybe one question just on the same slide that we are just seeing right now. As I understand, the Wasserstein metric would not converge quickly as quickly as, for example, the Euclidean norm, some similar norm. What is the consequence? The consequence would be that one can't use the Wasserstein metric in functions with only few data points. Is it correct? Can one say it like this?
Yeah, exactly. The issue is if you are in high dimension, it's just impossible to estimate Wasserstein distance accurately. So if you want to do it, you need to use some other idea. So maybe if you know, for instance, the distribution comes from very smooth densities or from a cube, maybe you might be able to leverage this. And this is what people are now working on, is to leverage other properties. But if you have no other ideas about your distribution, like alpha and beta, you don't really know what they are, then you are facing the first, the bound is sharp. And it's really if you can do the numerics, basically, even if it's like, let's say it's a Gaussian in high dimension and you want to estimate the optimal transport, you would see that the convergence is very slow. And I'm taking the Gaussian because for the Gaussian, you can actually compute in closed form the Wasserstein distance. So it's a scenario where you could compute the WP between alpha and beta exactly. And then you can compute it numerically, and you would see that the error you make is usually enormous and with a lot of variance. So you get a lot of errors, which basically is predicted by the theory.
I was asking for this because this is a limitation not of the exact algorithm that one uses, but it's limited directly of the matrix, as I understand. I was asking this because you mentioned in this context the Monte Carlo methods, I guess, and in that case it would be a part of the algorithm that introduces this either advantage or disadvantage. But as I understand now, it's here part of the metric, and it's not. One cannot go around it, kind of, by just taking a better algorithm.
Yeah, exactly. The limitation is even more severe than just the fact that an algorithm is not working. Is any algorithm you could come up with actually face from the same difficulty. So you can show that any method that would estimate WP from discrete sample would actually commit the same error. So you can see it's really not a problem of algorithm. It's just a problem of the distance itself. In some sense.
Okay. Thanks.
But of course, if you know more about alpha and beta, of course, there is no contradiction that if you know that alpha and beta are like very smooth, Like for instance, if you know that alpha and beta are densities which are derivable up to order D, so if you know that they are super smooth and very smooth according to the dimension, then it's easy to show that there are techniques to break the curse of dimensionality. One technique would be to simply replace the sample by smoothed Gaussian, and then you would break the curse of dimensionality. And one of the questions that I was studying in my team is whether you could break the curse of dimensionality with Synchron. And unfortunately, we showed that it's not possible, that at least Synchron is not able to leverage smoothness enough in order to break the curse of dimensionality. So it raises question of what should be algorithms that are efficient and that would be able to break the curse of dimensionality if you know that your distribution are very smooth, for instance. And there is some papers that have been actually published this year on this topic, and it's very interesting topics. Of course, it's very theoretical. It's not super important for application. In practice, Synchron seems to work great, but from a theoretical point of view, I think understanding how to break the curse of dimensionality and in what sense, and also with what algorithm, because there's many papers that says you can break the curse of dimensionality with this method, but it doesn't really come with a fast algorithm. And by fast, I mean less than n squared, is not so clear. So it's kind of the thing that many people, I mean, several teams are working on this year.
Just quick in between. I would be interested in this paper that you mentioned that was from this last year.
Yep.
My connection is not too good, so maybe we can continue afterwards. But
yeah, don't hesitate. Just send me an email, and I can send you a few recent papers that have been published on this question. And they propose to replace basically linear programming by semi-definite relaxation. So if it's something that maybe some of you are interested in, like sum of square relaxation method is something that have been used recently to enforce regularity in optimal transport. So it's very promising. And it's not my work, so I advertise not for my work.
Great. Thank you, Gabriel. It was a very nice talk. If there are any other questions, obviously, like feel free to send emails or like continue the offline conversation.
Yeah, of course.
Yeah.
Thanks to everyone for attending. And hopefully see you at some point, everyone.
Yeah. Thank you so much for coming to us, Ceres, and presenting. Thank you.
Bye. Bye, Barna. See you, everyone.
Yeah. Bye, everyone.